Deep Learning Part 7 Convolutional Networks. So far, every network we have built treats its input as a flat, featureless list of numbers. But an image is not a list, it is a grid with rich spatial structure. This part builds a network that finally respects that structure, and in doing so, it conquered computer vision. Let us start with what an image truly is. A grid of pixels, each one a number, or 3 for color, red, green, and blue. And here is the crucial fact: nearby pixels are deeply related. Edges, textures, shapes, they all live in small local neighborhoods. The meaning is in the arrangement, not in the individual values. Now try to feed that grid into an ordinary, dense network. Unroll a modest 1,000 by 1,000 image into a single column. That is 1 million inputs. Connect them to just 1,000 hidden neurons. And you have 1 billion weights in the first layer alone. Far too many to train, and worse, unrolling the grid throws its structure completely away. The fix is to build in 2 simple truths about images. First, locality, a feature like an edge, depends only on a small patch of nearby pixels, not on the whole image. Second, translation invariance. An edge is an edge wherever it appears. Bake these 2 ideas into the architecture and the network becomes vastly simpler and far, far smarter. Both truths come from a single operation, convolution. Take a small grid of weights, we call it a kernel, often just 3 by 3. Now slide it across the image, 1 position at a time. At each spot, multiply the kernel against the patch of pixels beneath it, and sum the result. 1 small kernel sweeping the entire image. That kernel is nothing exotic. It is just a tiny weight matrix. It computes a weighted sum of a local patch, which is exactly a neuron, but one that looks at only 9 pixels at a time. And the very same kernel with the very same weights is used at every position. Its pattern of weights decides what feature it detects. Watch a real kernel at work. This one has positive weights on the left and negative weights on the right. Slide it over a patch that is bright on the left and dark on the right. The weighted sum comes out to 30, a strong positive response. Slide it over a flat, uniform region and it sums to 0. This kernel detects vertical edges. Now sweep that 1 kernel across the whole image and record every response. The result is a brand new grid. We call it a feature map. It lights up brightly wherever its feature appears and stays dark everywhere else. 1 kernel produces 1 feature map, a map of exactly where its feature was found in the image. Here is the profound payoff. The same 9 weights are reused at every single position in the image. 9 numbers, not a billion. And because the kernel is shared, a feature is detected identically no matter where it sits. Locality and translation invariance both achieved for almost no parameters at all. 1 kernel finds 1 kind of feature, so naturally we use many. 1 for vertical edges, 1 for horizontal, others for corners, for curves, for blobs of color. Each kernel produces its own feature map. Stack all those maps together and the layer outputs a whole set of feature channels, a rich multi-view description of the image. 2 knobs control the sweep. The stride, how far the kernel jumps at each step. A larger stride skips positions and shrinks the output. And the padding, a border of zeros added around the image so the kernel can reach the very edges. Together, by a simple formula, they set the exact size of the output feature map. Between convolutions, we often deliberately shrink the maps. This is pooling. Take each small region of the feature map and keep only its maximum value. The map gets smaller, cheaper, and a little more forgiving. A feature detected slightly shifted still survives. Pooling adds a touch more translation invariance. Depth threads through all of this. A color image enters with 3 channels: red, green, and blue. Each kernel spans all of the input channels at once and outputs a single one. So a layer maps a stack of input channels into a stack of feature channels. The width in space shrinks, the depth in features grows. Now stack these layers and something beautiful emerges, a hierarchy. The very first layer finds simple edges. The next combines those edges into textures and corners. Deeper still, it finds object parts, an eye, a wheel. And finally, whole objects. The same learned feature hierarchy we first promised, all the way back in part 1. Each neuron deep in the stack sees only a small patch of the layer just below it. But that patch already summarizes a larger patch beneath it, and so on downward. So the region of the original image that a deep neuron responds to, its receptive field grows with depth. The late layers effectively see the entire picture at once. Now assemble all the pieces into a full network. Convolution, activation, pooling, repeated, growing deeper and richer at every stage. Then at the very end, flatten the small, deep feature stack into a vector. Feed it into a few dense layers and a softmax. From raw pixels to a class label, that is a convolutional network. Let us count the savings once more. A dense first layer on our image needed 1 billion weights. A convolutional layer with 64 kernels, each just 3 by 3, needs only a few hundred. Orders of magnitude fewer parameters, and a far better match to the data. Fewer weights and yet better results. This idea has a proud lineage. From the first small handwritten digit readers, to the network that stunned the field on ImageNet in 2012 and launched the modern era. Then ever deeper designs made trainable by skip connections. Convolutional networks turned computer vision almost overnight into a solved enough problem. And we can look inside a trained one. Visualize the first layer's kernels and you find edge detectors and color detectors, emerged not designed. Look deeper and the features respond to textures, then to object parts. Nobody programmed any of this. It all fell out of minimizing the loss. Representation learning made beautifully visible. Step back and see the real lesson here. The convolutional network wins because its very structure matches the structure of images. Locality and translation invariance, built directly into the architecture. The right inductive bias for the right kind of data beats raw brute size. Hold onto that idea, it matters for what comes next. And convolution is not only for images. The same idea, a small shared filter sliding across structured data, applies far more widely. Slide it in one dimension over audio or over time series. Slide it over the nodes of a graph. Wherever local patterns repeat across a structure, convolution is a natural fit. But convolution has a built-in limit. It is fundamentally local. Each kernel sees only a small neighborhood at a time. To connect two things far apart in the image, the signal must travel up through many layers. For images where meaning is mostly local, that is perfectly fine. But for some kinds of data, locality is exactly the wrong assumption. Think about language. In a sentence, a word can depend on another word 20 or 50 positions away. A subject and its verb, a pronoun and its noun. There is no fixed local window that captures these links. The dependencies are long, and they can reach from anywhere to anywhere. So we need a different mechanism. One where every position can look directly at every other position. No fixed window, no waiting to travel up through layers. Instead, direct learned connections across the entire input all at once. That mechanism has a name, attention, and it is the heart of the finale. One honest note on where things stand. For years, convolution ruled computer vision completely. Today, that same attention mechanism has entered vision too, in models called vision transformers. The two ideas now compete and combine. But the core insight of convolution, matching the architecture to the data, remains absolutely foundational. And notice how little actually changed. A convolutional network is still a differentiable parameterized function. Still trained by minimizing a loss, still with gradients from backpropagation, still followed downhill by gradient descent. We only changed one thing, the shape of the layers, to match the shape of the data. We have conquered the grid. Images with their local repeating structure now have an architecture built precisely for them. But language is not a grid, it is a sequence, where any word can depend on any other. To handle that, we need our final and most powerful idea. So part 7 in one line. Convolutions share small kernels across an image to detect features cheaply and build them into a hierarchy. The right architecture for the right data. Next, the finale, the architecture behind every large language model, part 8, attention and the transformer.